Test.
Okay, the next speaker is Bas Westerbaan. Again, can I be him?
Okay. Thank you for having me. Thank you for being here so early. Does anyone know how to turn this off? Any other users?
Yeah. Hi.
Does anyone know?
Like the pause button or something to share that on the screen.
Because this. Oh, the pause. Thank you. And now this doesn't work anymore. Oh, yes. I hope it will. Thank you again. So this is joint work with Sander. Sander, where are you? He's there. Okay. This work began when we saw an article by a group of people at Oxford who wrote an article which could have been called "The Kochen Specker System has at least 80 vertices," and we got hooked on it. It was really a great read, and to prove this bound, or their bound already, required a mix of elementary mathematics and computer science. So with some simple ideas, you can get a lot further with this problem. So this is why I'm thoroughly excited by it, and I hope you will find it fun as well. Okay, so there's Kochen Specker here, but it isn't really about Kochen, it's just actually mathematics and computer science. So let's recall what a Kochen Specker system is. So it's about measuring the spin of a spin 1 particle. So how could you do this? You can have a certain magnetic field and put a spin 1 particle, for instance deuterium, shoot through it in a certain direction. So you measure a spin in a certain direction. And depending on its spin, it will either go through without deviating or it will deviate. So quantum mechanics predicts the chance, just the chance, that such a particle with a given direction will deviate or not. So one could wonder, is there a deterministic theory predicting whether the particle will deviate or not? And Kochen Specker says, well, it must be very odd, indeed. So how do they do this? So why, in what way must it be odd? It must be odd in the way that normally we have the empirical fact that if we measure the spin in 3 orthogonal directions, in 2 of them it will deviate, and in the other one it will go straight. So in 2 of them it will be 0, and in 1 of them it will be 1. And Kochen Specker proved that you cannot have such an assignment of such a deterministic theory that will obey this empirical fact. So more concretely, they showed it by giving a set of points on the sphere. So a point is a direction. So the line through the origin and through the point gives a direction. And it doesn't matter if it's the point or the other direction, it's all the same. So I identify points which are antipodal. And so a deterministic theory is a coloring of points of the sphere, such that for any 3 orthogonal points, 2 of them are colored 0, and exactly 1 of them is colored 1. And so they showed that you can have a finite subset of the sphere, a finite number of points, such that you cannot have such a coloring. So I call such a coloring a 0, 1, 0 coloring. I just color it. Okay, so the first one was contained 117 points. And later people tried to find smaller ones. So Penrose and Perez independently found a smaller one of 31, quite some time later. And then also Conway, Lee Conway, also weighed in and found one of 31. And Conway was quite interested in these Kochen Specker systems because he uses a Kochen Specker system in his proof of the strong free will theorem. And in the series of lectures, about the strong free will theorem, it encouraged the search for smaller Kochen Specker systems. So Watling, so this is a group from Oxford, Aaron Wampler. Watling attended such a lecture, and I guess that's where he got the idea to look at it. So in 2009, so this is the article I referred to in the beginning of my talk, they showed that it has at least a minimal Kochen, the smallest Kochen Specker system must have at least 18 points. And we improved this to 21. And we've got another computation running, and hopefully in a month we can say we improved it to 22. Or we found the Kochen Specker system of 22. Okay, so how did Arends, Wampler, and Watling do this? Well, oh yeah, this is Conway's record. So this is the record of Conway of 31 points. So here you see the sphere, and this is a box around the sphere, and you should project every point onto the sphere. And then you have 31 points on the sphere, and these are the current records of the smallest Kochen Specker system. So how do they solve?
Excuse me. Just a quick question. Why is it important to find the smaller set? What's the significance of it?
Well, I did because I like the problem. I find it quite entertaining. The Oxford people give arguments why it would be interesting. So a lot of correlations. So if you take the Kochen Specker vector systems, then usually if you look at properties, then they tend to have very non-classical properties. So there are quite some articles which use Kochen Specker systems to get non-classical correlations and things like that. But I think if a problem is interesting and fun, then you should look at it anyway. And of course the authority argument that Conway himself thought it was a great problem. Okay, so how did they do this? How did they find the lower bound of 18? So they reduced the problem, they recognized that it's really a problem about graphs. So if you have a Kochen Specker system, so the points on the sphere, then it's not really important where these points lie exactly, it's only important which points are orthogonal. So if you have a set of points on the sphere, you can form this orthogonality graph. The vertices are the points, and they are adjacent if they are orthogonal. So but not every graph occurs as orthogonality graph. So I say a graph is embeddable if it occurs as a subgraph of the orthogonality graph of some set of points on the sphere. So embeddable on the sphere. And I say it's a 0, 1, 0 colorable if every triangle, so that's an orthonormal basis, is colored exactly once 1 and twice 0, and no adjacent vertices are both colored 1. So now the point is that there is a Kochen Specker system on n points, if and only if there is a graph on n vertices that's embeddable and not 0, 1, 0 colorable. So what did they do? They just enumerated all graphs as far as they could do it computationally, checked whether it's 0, 1, 0 colorable, and then checked whether it's embeddable. And they found none which were non-0, 1, 0 colorable and embeddable, so they concluded there cannot be a Kochen Specker system of 17 points or less. And well, enumerating all graphs, that's a little bit too much, because so the amount of non-isomorphic connected graphs on 18 vertices is 10 to the power 26. So they didn't do this, that's way too much. Oh, by the way, we can assume that the minimal Kochen Specker system, of the graph at least of it, we may assume it's connected, because if it's not connected, then it has two components. One of the components must be non-0, 1, 0 colorable, and that component is also embeddable. So we can assume it's connected. So but we can reduce it even more. We can assume it doesn't contain a square. So and it's reduced this significantly. So what can we assume is? Well, if we have a square in the orthogonality graph, then V is orthogonal to the same points as W. So if you have V, then the points orthogonal to it is the great circle, which is for which V is the normal, and W has another great circle, and so this point is fixed by the intersection of the great circles, and there are only two intersections if V and W are different. But we identified antipodal points because there is only one a point which can obey this. So these two had to be equal. Plot one. So we know it's square free, and this is really a considerable restriction. And so they looked at connected square free graphs, and we found another restriction, namely that it must have minimal vertex degree 3. So why is this? Well, suppose we have a 0, 1, 0 colorable graph, and we add a point which is connected to at most two other points. Well, then this new graph is 0, 1, 0 colorable. Why? Two cases. Either this point isn't in a triangle or not. If it's not in a triangle, then we can color it 0. There's no problem. Coloring it 0 is always fine. If it is in a triangle, then we look at the coloring of the triangle in which it's in. If there are two zeros in the other edges, then we must color it 1, and otherwise we can color it 0. So, by contraposition, we know that if we have a non-zero 1, 0 colorable graph with a point which has at most vertex degree 2, then we can just remove it, and we still have a non-zero 1, 0 colorable graph, which is still embeddable. And this really cuts it down, and this is how we got to 21 and 22 instead. I must note that they actually also noted this restriction in their article, but for some reason, in one place, but for some reason they didn't use it in their computation. And so, to get even further, we need another restriction to get to. So I also can prove that the minimal Kochen Specker system, or the graph at least of it, must be biconnected, so we can remove any edge and it's still connected. That's biconnected. So that has a few proof, but it doesn't really cut down the number of graphs to consider. But maybe if I have time, I will tell it. Okay, so this is what we got from our computation. We found so up till 17 is what the Oxford people already found. So a candidate is a non-0, 1, 0 colorable graph, which we consider. And they found just, so they found it up until 17. So there's only one graph on 17 vertices or less that is not 0, 1, 0 colorable. And the big problem with which Arendts, Wemple, and Wagner struggled was determining whether this graph is embeddable or not. If it is embeddable, then it's a 17-point Kochen Specker system. If it's not embeddable, then we know that there cannot be a 17-point Kochen Specker system. So they really struggled with proving the embeddability or non-embeddability of those. So we found quite some candidates, so non-0, 1, 0 colorable graphs. And this one is, so this is our result which we fit, and this is about 3/4 through the current computation. So, so how did they prove that this graph was not embeddable? Well, they used integer. So what they did is they for every point they said, well, it must be somewhere in the box, on the sphere somewhere, and then they divided up the sphere in two parts. So it's either on the left part or the right part of the sphere. Well, let's assume it's on the left part of the sphere. Then we can deduce that maybe some other points must be in a smaller part of the sphere. And by backtracking, so by continuously trying all possible ways and splitting it again and again, they have computer-aided proof that this single graph, this 17-point graph, is not embeddable. But if you would write it down on paper, it would be really a big stack of paper. So we tried to prove it by hand. And we succeeded. This was the first attempt. And you just give it variables and you go calculating, and finally you find a contradiction. And you don't use the whole graph to come to this contradiction, you only use a small subgraph. And this led us to these three graphs. These three graphs are not embeddable. So the first two, the Oxford people also recognize as not embeddable. These three are not embeddable. And every of the candidates we found contain one of these three as a subgraph. And thus they are not embeddable themselves. We can do better than what I showed on the previous slides. There's a huge proof to do this. So we looked at this graph, and I'll prove it's not embeddable. Well, let's suppose it is embeddable. Now we'll give it some names, so Z in the middle, and X, A, D, and then P1 up to P5 around. Note that P1 is orthogonal to V, and P1 is orthogonal to A. So V and A are somewhere on the sphere, and P1 must be the intersection of the two great circles for which A and V are normals. And we actually have a good expression for P1, namely, it is the cross product of V and A. Well, not exactly the cross product, because the cross product doesn't have to lie on the sphere again, but it's collinear. It's on the same line as the cross product of V and A. So then we can write P1 is V cross product A, and then we can write P2 is V cross V cross A, and P3 is W cross V, etc. And so we go around the graph, and we see that that A must be collinear to this thing. And now we can assign some more explicit coordinates, and then you get that this collinearity comes down to this. And you just write it out a little bit, and you see that we must have that this is equal to 1, and by Cauchy-Schwarz we see that this cannot be the case. But it's not too hard with this. I don't think in the morning is the best time to go through it thoroughly. But this is really, it's an independent paper. But the great thing is, we can actually optimize this. We can, so given a graph, we can pick some fixed points and chase through the graphs, assigning points cross-product expressions. And then we get a formula in the language of the reals, which is there are assignments of, there are real numbers which are coordinates for the points in the sphere, such that these relations hold you derive while chasing through the graph. And so for this graph, we did this. So we brought to this. This is an example of the expression, the formula in the language of the real numbers, which you will get for the previous graph I showed, but then optimized. So this is for the reduced algebra package, and so I just wanted to show that you can actually do this. And in this way, we actually could decide for all of the graphs we were interested in whether they are embeddable or not by chasing to assigning cross products to the points, then deriving such a formula, and then using Tarski's quantifier elimination to decide whether it is true or not. Okay, so let's see how much time I've left. Okay, so I've put the source code and the results on the website, which is hopefully easy to remember. And I want to encourage you to look at it yourself in your spare time, because one simple idea like minimal vertices degree 3, and you can get much further. I think we can solve this with 2 more ideas. Sandra and I have a bet. I think there is a Kochen Specker system on less than 25 points. He thinks there are more than 25. I should also mention Bockman, so a professor from Oxford, thinks that the 31 is the smallest because it shows up every time when he tries to find it by generating random graphs. But I think that might be smaller. And so there are a lot of also small little problems which I don't know which you think. For instance, I call G embeddable if it's a subgraph of the orthogonality graph of some points on the sphere. But is it the case that if G is embeddable, it actually is equal to the orthogonality graph of some points on the sphere? I don't know. I think it's with some algebraic geometry you solve this on basic. Also, the Kochen Specker one was given by points on the grid, so on the cube on the grid. For all we consider, the embeddable graphs seem to be also embeddable on such a grid, but is there a counterexample? I think it should also be solved, maybe using Galois theory or something like that. So, okay. Thank you.
Thank you.
I have a technological question. So you said you use point-by elimination.
Yes.
Which program do you specifically use, like Mathematica or Maple or what?
No, Mathematica structured it.
Okay, hi.
I use I tried several packages. So now I use the redlog package.
Say it again.
The redlog package of the reduced algebra system. So redlog
Okay.
of the reduced algebra system.
I see. Thanks.
So in the strategy of excluding particular graphs, do you think perfect graphs are in special order?
Oh, please recall for me what the perfect graph is.
So they would be graphs where whenever you do a subgraph, the number of the largest peak is equal to the chromatic numbers, the number of colors you need. I mean, the question is not a random question because for some other problems in contextuality where you try to find bounds on contextuality, perfect graphs are essentially they are those for which you don't have a violation of classical contextuality.
Okay.
So the intuition would be that then they would be graphs that you would also rule out if the intuition carries, and I think it should.
But there aren't many cheeks, I may note, because there aren't squares.
I'm sorry?
There aren't squares, so there aren't big cliques. But we could, I would like to discuss it later on. So, thank you.
Any other questions, comments? Yes, big item.